Welcome! In this session, we'll dive into a fascinating problem: split array into Fibonacci sequence. We'll explore how to approach this problem, break it down into manageable steps, and consider different strategies to solve it effectively. Let's get started. The problem asks us to split a string containing only digits into a sequence that follows the Fibonacci-like property. This means the sequence must consist of at least three integers where each number is the sum of the two preceding numbers. For instance, if we have numbers a1, a2, and a3, then a1 plus a2 must equal a3, and this rule continues for the entire sequence. Additionally, there are some important constraints to keep in mind. First, no number in the sequence can have leading zeros, except for the number 0 itself. Second, every number in the sequence must fit within the range of a 32-bit signed integer, which means it must fall between -2 to the power of 31 and 2 to the power of 31 1. Lastly, the numbers must be derived from the string in the order they appear, from left to right. If it's not possible to create such a sequence, we need to return an empty list. The output for this problem is straightforward. If we can successfully split the string into a valid Fibonacci-like sequence, we return the sequence as a list of integers. Otherwise, we return an empty list to indicate that no valid sequence can be formed. Let's look at an example to make this clearer. Suppose the input string is 1 2 3 4 5 6 5 7 9. Here, we can split the string into the sequence 123, 456, 579. This sequence satisfies the Fibonacci-like condition because 123 plus 456 equals 579. All numbers are in order, there are no leading zeros, and they fit within the 32-bit integer range. This means 123, 456, 579 is a valid output. Here's another example to illustrate the problem. Consider the input string 11235813. We can split this into the sequence 1, 1, 2, 3, 5, 8, 13. This sequence is valid because each number is the sum of the two preceding numbers. Specifically, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. There are no leading zeros in any of the numbers, and all of them fit within the 32-bit integer range. Since the sequence satisfies all required conditions, the output is 1, 1, 2, 3, 5, 8, 13. Let's look at another example. If the input string is 110, 1111, we can split it into the sequence 11, 0, 11, 11. This sequence satisfies the Fibonacci-like condition because 11 plus 0 equals 11, and 0 plus 11 equals 11. The numbers are in order, there are no invalid leading zeros, and all values fit within the 32-bit integer range. Since the sequence meets the criteria, the output is 11, 0, 11, 11. These examples demonstrate how to derive a valid sequence, provided the conditions are met. Finally, let's review the constraints and edge cases. Every number in the sequence must fit within the 32-bit signed integer range, which spans from -2 to the power of 31 to 2 to the power of 31 1. The input string must also allow for at least three integers to form a sequence. For instance, if the string is too short, such as 1 or 12, it's impossible to create a valid sequence, so the output would be an empty list. Similarly, if the string contains digits that would lead to invalid splits due to leading zeros, like 1023, we return an empty list because 1, 0, and 23 don't satisfy the Fibonacci condition. Lastly, even if the sequence starts out valid, we must ensure that no sum exceeds the 32-bit integer limit. If any of these conditions are violated, the result is an empty list. These constraints ensure that the solution is both valid and robust. To start, let's consider the brute force approach. The idea here is straightforward: generate all possible ways to split the input string, number, into at least three integers, and then check whether each sequence satisfies the Fibonacci property. The property requires that every number in the sequence is the sum of the two preceding numbers. While this method is simple to conceptualize, it quickly becomes impractical. The reason lies in the sheer number of possible splits, which grows exponentially as the length of the string increases. This makes the brute force approach computationally expensive and unsuitable for larger input sizes. Although it's easy to implement, the trade-off is poor performance, as it doesn't scale effectively for real-world use cases. Now, let's focus on the backtracking approach, which is the chosen strategy here. Instead of blindly generating all possible splits, this method incrementally constructs the sequence, ensuring it adheres to the Fibonacci rule at each step. The approach utilizes a few key observations to reduce unnecessary computations. For instance, the sum of the first two numbers in the sequence determines the third number, allowing us to avoid exploring invalid splits early. Additionally, Fibonacci numbers grow quickly, so we know that any number in the sequence cannot start with a leading 0 unless it's the single-digit 0, and it must fit within the range of a 32-bit signed integer. In terms of implementation, we iterate through possible lengths for the first two numbers and use recursion to build the sequence. At each step, if the sum of the last two numbers matches the next segment of the string, we proceed; otherwise, we backtrack and explore other splits. The process continues until the string is fully consumed, and the sequence contains at least 3 numbers. There's also an alternative iterative approach to consider. Instead of recursion, this method uses 2 nested loops to fix the first 2 numbers and then simulates the rest of the sequence iteratively. While this eliminates the overhead of recursion, it comes with some trade-offs. The iterative approach is less flexible when the sequence fails mid-construction, as it doesn't support early backtracking. Because of this limitation, we ultimately chose the backtracking approach. Backtracking strikes a balance between simplicity, flexibility, and efficiency. Unlike brute force, it avoids exploring invalid splits, and unlike the iterative method, it dynamically adjusts when constraints are violated. This results in a far more efficient solution for generating Fibonacci-like sequences from the input string. However, it's worth noting that backtracking is slightly more complex to implement compared to the iterative method, which is more straightforward but less adaptable. Finally, let's examine the complexity of our chosen approach. The time complexity is O(n squared, where n represents the length of the string. This is because we explore all possible pairs of starting numbers, which takes O(n squared, and validate the sequence as we build it. The space complexity is O(n), primarily due to the recursive call stack and the storage required for the sequence. Overall, this approach balances correctness and efficiency by leveraging the problem's constraints to minimize unnecessary computations. The combination of early pruning and recursive exploration allows us to construct Fibonacci-like sequences effectively and efficiently, making this a practical solution for the problem at hand. To solve the problem of splitting a string into a valid Fibonacci sequence, we start by understanding the core requirement. A Fibonacci sequence is a sequence of numbers where each number is the sum of the 2 preceding ones. For example, 1, 1, 2, 3, 5, and so on. The first step in our algorithm is input validation. If the length of the input string, number, is less than 3, we can immediately return false. This is because at least 3 numbers are required to form even the smallest Fibonacci sequence. This early check helps eliminate invalid cases up front, saving unnecessary computation. Now, the next step involves iterating over possible combinations for the first 2 numbers in the Fibonacci sequence. To achieve this, we use 2 nested loops. The outer loop determines the endpoint of the first number, denoted by I, and the inner loop determines the endpoint of the second number, denoted by J. These indices allow us to partition the string into 2 substrings, number, I, for the first number and number, ij, for the second. However, these substrings must meet certain constraints. They cannot have leading zeros unless the number itself is 0, and they must be convertible to integers within valid ranges. Once valid integers a and b are derived, we start generating the Fibonacci sequence. Using these initial numbers, we iteratively compute the next Fibonacci numbers and compare them to the subsequent digits in the string. For each computed Fibonacci number, we extract the next substring from number and check if it matches. If no match is found, we abandon the current combination and move to the next pair of starting numbers. If the entire string is consumed while matching the Fibonacci sequence, we conclude that the string represents a valid sequence and return true. When no valid Fibonacci sequence is found after trying all possible combinations, the algorithm returns false. This ensures that every potential split has been exhausted before concluding failure. A key insight here is the use of backtracking combined with constraints. While the generation of the Fibonacci sequence can be recursive, an iterative approach is often sufficient and more efficient. By applying constraints, such as checking for leading zeros and ensuring numbers remain within valid ranges, we significantly reduce the number of invalid combinations early in the process. Additionally, the exponential growth of Fibonacci numbers naturally limits the search space, as numbers larger than the remaining length of the string cannot possibly form valid splits. This optimization ensures that we focus only on feasible combinations without exploring redundant paths. Finally, the use of substrings to generate potential numbers is memory efficient, as we do not need to store all combinations explicitly. Instead, indices and a few integer variables are sufficient to manage the process. Key operations in the algorithm include substring extraction, integer conversion, and prefix matching. Extracting substrings is efficient and happens in constant time for each split, making it ideal for this problem. Converting these substrings into integers allows us to perform arithmetic operations like summing two numbers to generate the next Fibonacci number. However, this step also introduces edge cases, such as leading zeros, which must be handled carefully. Prefix matching ensures that the next Fibonacci number aligns with the corresponding part of the string, which is a quick and direct operation. In terms of complexity, the algorithm has a time complexity of O(n cubed). This is due to the nested loops that explore all possible splits for the first two numbers, which is O(n squared), and the generation and verification of the Fibonacci sequence for each split, which is proportional to n. The space complexity is O(1), as no additional data structures are used beyond the input string and some integer variables. This makes the algorithm efficient in terms of memory usage, even for larger input strings. This implementation solves the problem of splitting a string into a Fibonacci-like sequence. The function split into Fibonacci takes a string number and attempts to find a valid sequence. First, the helper function is _valid_part validates substrings to ensure they don't start with a 0, unless they are 0, and that they are within the 32-bit integer limit. This prevents invalid numbers from being used in the sequence. The backtrack function recursively attempts to build the Fibonacci sequence. It starts by iterating from the current start position, extracting substrings part up to the end position. If the substring is not valid, the loop breaks early for efficiency. The integer value of the substring, part_number, is then checked against the Fibonacci property. If the last two numbers in the path exist, their sum must equal part_number. If the condition fails, the loop continues. If the substring satisfies the conditions, the function recursively tries to extend the sequence by calling backtrack with the updated start and the extended path. If a valid sequence is found, it is returned. Finally, the main function initiates the backtracking process and ensures that the result is returned as an empty list if no valid sequence is found. This approach combines backtracking with validation to efficiently explore possible splits and construct a Fibonacci sequence. Here, we begin by defining the split into Fibonacci method, which takes a string number as input and attempts to split it into a Fibonacci-like sequence. We initialize an empty list called result to store the sequence. The key logic lies in the backtrack method, which we call with the starting index, the input string, and the result list. If the backtracking process is successful, we return the result, otherwise, we return an empty list. Now, looking at the backtrack method, we see that it first checks if we've processed the entire string and if the sequence has at least 3 numbers. If so, it returns true, indicating that a valid sequence has been found. Next, we enter a loop to explore potential substrings of number, starting from the current start index and extending to every possible end position. Within the loop, we extract the substring part and check if it's valid using the isValidPart method. If it's not valid, we break out of the loop. If it is valid, we convert the substring into an integer, part number. We then check if adding this number would maintain the Fibonacci property, which requires the last 2 numbers in the sequence to sum up to the current number. If the condition isn't met, we skip this number and continue the loop. If it meets the condition, we add part number to the sequence and recursively call backtrack with the updated index and sequence. If this recursive call returns true, we propagate that result upward. If not, we backtrack by removing the last number from the sequence and continue exploring other possibilities. Finally, the isValidPart method ensures that the substring has no leading zeros, is within the bounds of a valid 32-bit integer, and doesn't exceed the length constraints. This helps filter out invalid parts before further processing. Here we start with the input string number equals 11235813. The first step is initialization, where we call the backtrack function, passing in the starting index as 0 and an empty path list. This path will store the numbers as we build the Fibonacci sequence. Next, we begin looping over possible partitions of the string from int equals 1 to 8. For the first partition, we extract the substring number 0:1, which is 1. This is valid because single-digit numbers are allowed, and there are no leading zeros. We convert this part to an integer, resulting in 1, and add it to our path, making the path 1. At this point, we make a recursive call to backtrack, advancing the start index to 1 and passing along the updated path. Now, with the start index at 2 and the path containing 1, 1, we continue partitioning. We extract the substring number 2:3, which gives 2. This is a valid number as well, so we check if it matches the sum of the last two numbers in the path. The sum of 1 and 1 is indeed 2, so we add this number to our path, resulting in 1, 1, 2. Another recursive call is made, moving the start index forward to 3 and continuing with the updated path. Repeating this process, we extract and validate numbers 3, 5, 8, and 13, ensuring each matches the Fibonacci property. Eventually, the path grows to 1, 1, 2, 3, 5, 8, 13. Since we've used up the entire string and the sequence is valid, we return this result. Next, let's consider the input number equals 1, 2, 3, 4, 5, 6, 5, 7, 9. Again, we start with a call to backtrack, initializing the start index at 0 and the path as an empty list. For the first partition, we extract the substring number 0:1, which is 1. This is valid, so we convert it to an integer and add it to the path, resulting in 1. We then make a recursive call to continue. As we progress, we extract 2 and then 3, building the path to 1, 2, 3. At each step, we check if the current number is the sum of the last two numbers in the path. Continuing this process, we eventually extract and validate the numbers 5, 6, and finally, 579. At the end of the string, we have the complete sequence, 123, 456, 579, which satisfies the Fibonacci condition. This sequence is returned as the output. For the input number equals 0000, we start again by calling backtrack with an empty path. This time, we encounter a string of zeros. As we loop to form partitions, the substring 0 is extracted. This is valid since a single 0 is allowed, and it's converted to an integer before being added to the path. The path becomes 0. We then proceed with recursive calls, extracting additional zeros, resulting in 0, 0, 0. Since all zeros form a valid Fibonacci sequence where each number is the sum of the previous two, the sequence 0, 0, 0 is returned as the output. In this problem, the time complexity is primarily determined by the recursive backtracking approach that we use to construct a valid Fibonacci sequence. First, let's consider the outer loop, which is responsible for splitting the input string into potential substrings. For each starting index, the loop iterates over all possible substrings by varying the ending index. With n possible starting points and roughly n substrings per starting point, this results in n squared substring generation. Next, each substring undergoes validation to ensure it meets specific criteria. It must not have leading zeros, and its numerical value must be less than 2 to the power of 31. This validation takes k time, where k is the substring's length, which is at most 10, as it's bounded by the maximum value of 2 to the power of 31. After validation, we check whether the substring can extend the Fibonacci sequence using simple arithmetic, which is an O1 operation. Finally, the recursive backtracking step explores all valid extensions, potentially generating all combinations of valid Fibonacci sequences. This exploration is the most computationally intense aspect of the algorithm. Now, considering the overall time complexity, the worst-case scenario occurs when every possible substring is valid, which means the algorithm must explore all potential combinations. For each starting index, this can lead to 2 to the power of n recursive paths in the worst case. Combining this with the n squared substring generation, the total time complexity becomes n*2 to the power of n. Shifting focus to space complexity, the first component is the recursive call stack. The depth of recursion corresponds to the length of the sequence being constructed, which in the worst case is proportional to n, resulting in a maximum stack space of O, n. The second component is the path list, which stores the current Fibonacci sequence being built. Its maximum size is also proportional to n, as it depends on the length of the input string. Together, these two components contribute to a space complexity of O, n. Additionally, there's the temporary storage used for substrings during validation. The part variable holds the current substring being processed, and its size is proportional to the length of the substring. Since the maximum length of any substring is bounded by O log 2 to the power of 31, this results in a constant memory usage of O, 1. When we combine all the components, the recursion stack, the path list, and temporary storage, the overall space complexity remains O, n. Comparing this backtracking approach to a brute force method, we observe that brute force would generate all possible substrings, validate each combination, and check if it forms a Fibonacci sequence. This would result in a staggering complexity of O, n cubed asterisk 2 to the power of n, in the worst case due to the combinatorial explosion. In contrast, the backtracking method avoids redundant computations by pruning invalid paths early, achieving a much more efficient O, n asterisk 2 to the power of n, in the worst case. The recurrence relation for backtracking can be approximated as T, n, equals n asterisk T, n1, which simplifies to O, 2 to the power of n. Including the O, n squared, substring generation, the final time complexity becomes O, n asterisk 2 to the power of n. Finally, let's examine the best, average, and worst case scenarios. In the best case, if the input string cannot form any valid Fibonacci sequence, the algorithm terminates early, with a time complexity of O, n squared, due to substring generation alone. The average case is more nuanced, as it depends on the number of valid paths the algorithm explores. Typically, due to early pruning of invalid paths, the average case is closer to O, n asterisk 2 to the power of m, where m is smaller than n. In the worst case, the input string perfectly matches a valid Fibonacci sequence, leading to maximal recursion depth and a time complexity of O, n asterisk 2 to the power of n. This comprehensive analysis highlights the efficiency of the backtracking approach in pruning unnecessary computations while still addressing the exponential growth inherent in exploring Fibonacci sequences. When solving this problem, there are some common mistakes that can trip you up. First, handling leading zeros incorrectly is a frequent error. Numbers like 01 foot or 001 are not valid integers in a sequence, so you must explicitly check for and reject partitions that start with a 0 unless the number itself is just 0. Next, integer overflow can be a concern, especially when working with very large numbers. If the input involves numbers greater than 10 to the power of 10, using data types with limited size, such as int in Java or C++, could lead to overflow. To avoid this, use larger data types like long, big integer, or rely on Python's default int, which handles arbitrary precision. Another issue is skipping edge cases. For example, if the input string is empty, too short to form a sequence, or only contains two numbers, your code should gracefully handle these scenarios. Lastly, inefficient search techniques can significantly slow down your solution. If you're using nested loops or exploring all partitions without pruning invalid ones early, the runtime can quickly become exponential. Focus on optimizing by stopping recursion as soon as a sequence violates the Fibonacci property, which will save considerable time in larger cases. Another pitfall to watch out for is defining the base case incorrectly in your recursion. If your stopping condition doesn't ensure that the entire string is used and the sequence contains at least 3 numbers, your solution might either produce incorrect outputs or run into infinite loops. Let's discuss some insights for interviews. Recognizing patterns is crucial, as interviewers often look for your ability to identify that a Fibonacci-like sequence relies on the sum of the previous 2 numbers to match the next. Leveraging this property early can help you validate sequences and prune unnecessary checks. Recursion is a natural choice for this problem since it aligns with partitioning, but you should be ready to explain how you manage the recursion stack and why your approach avoids redundant computations. Optimization techniques, such as breaking early when the sum of 2 numbers exceeds the length of the remaining string, will demonstrate your ability to write efficient code. Finally, it's always a good idea to highlight edge cases during your explanation. For instance, you could bring up specific examples like 112,358, which is a valid Fibonacci sequence, or 000, which requires special handling due to leading zeros. This problem is also closely related to several other problems on LeetCode. For example, LeetCode 306, additive number, generalizes the concept to additive sequences beyond Fibonacci, where each number in the sequence is the sum of the previous two but isn't restricted to the Fibonacci pattern. Another direct variation is this very problem, LeetCode 842, which focuses specifically on splitting an array into a Fibonacci sequence. LeetCode 43, multiply strings, might seem unrelated at first, but it shares challenges like parsing strings into numbers and managing large integers, making it a good practice problem for handling edge cases. Lastly, LeetCode 39, combination sum, involves a similar backtracking approach, where you look for valid combinations that meet certain constraints. Exploring these related problems can deepen your understanding of partitioning, recursion, and edge case handling, which are central to this problem. There are also alternative approaches you can consider when tackling this problem. Iterative backtracking, for instance, replaces recursion with an explicit stack to manage partitions. This avoids issues with recursion depth limits, though it does require you to handle the stack manually. Another option is using dynamic programming, which could store valid partitions and build solutions iteratively. However, DP is generally less intuitive for Fibonacci sequence problems due to the dependency on previous values. A greedy approach is another possibility, where you start with the smallest valid numbers and build the sequence greedily. While this can be faster, it has the drawback of potentially missing valid partitions because it doesn't explore all possibilities. Each approach comes with trade-offs. Brute force, while simple, is highly inefficient with a time complexity of 2 to the power of n in the worst case. Backtracking with pruning strikes a balance between simplicity and efficiency, making it the most commonly used approach for this problem. DP and greedy methods, while more specialized, may be less flexible for variations of the problem. Choosing the right approach depends on the specific requirements and constraints of the scenario you're solving. Great job! To wrap up, we covered the key aspects of solving the split array into Fibonacci sequence problem. We discussed the algorithm, its complexity, and major takeaways. Remember, practice makes perfect. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!